Okay, now we're recording and we're ready to start with question 1, which is a sample of iron sulfide is found to have an iron-sulfur mass ratio of 1.16 to 1. How many grams of sulfur are contained in 3.5 grams of the sample? So in this case, we don't know the exact formula for iron sulfide. Iron is a transition metal, so we can't possibly know what its charge is unless it's told to us. So if we had the chemical formula, this would be a different and perhaps simpler problem, but it's really not that bad. We're just using mass ratios here. This is sort of along the concept of the law of definite proportions. So our sample here is 1.16 to 1 iron to sulfur in terms of mass. And so we can think of this as a ratio. Our compound contains 1.16 grams of iron for every 1 gram of sulfur. And then if you want to think about, well, how much is that per mass of compound, remember the mass of the compound is just the sum of the elements, so per 2.16 grams of compound. So we now have two ratios for our iron sulfide, which they'll call FeXSY, because we don't know the exact formula. But what this means is that we have 1.16 grams of iron per 2.16 grams of compound. We have 1 gram of sulfur per 2.16 grams of compound. And now we can just use this ratio as a simple conversion factor. So when we give you mass amounts or mass percentages, don't forget that they can be used as ratios and conversion factors. So if we're looking for the grams of sulfur in this sample, we have 3.50 grams of our compound. And then from this information up here, we see that we have 1 gram of sulfur for every 2.16 grams of the compound. Which then comes out to 1.62 grams. All right, so the law of definite composition tells us that this particular compound is going to have this ratio of masses, and it doesn't matter how much compound we have, that ratio applies to any amount of the substance. All right, any questions on that one? That was a pretty straightforward mass laws. There's also, just to be aware, some conceptual stuff about mass laws that we should be aware of. And then some of the key players, the early scientists that came up with this stuff. Be familiar with some of the names, just the ones that are in the notes mostly. So things like Dalton's law and Lavoisier and those people. So review that on your own, but there's going to be a little bit on history, but not much, and it's just going to be the basics. Okay. Okay. All right, and then the next question deals with isotopes. So we want to know the number of protons, electrons, and neutrons in the following isotope. Molybdenum with 9642 is the symbol. So what we have to remember for these ones is the anatomy of an atomic symbol. We haven't seen this in a while, but if you have an atomic symbol, you give the abbreviation for the element, and then you have Z on the bottom and A on top. Now what we should realize too is sometimes we leave out Z for reasons I'll get into, but Z is the atomic number, which is the number of protons. So we abbreviate protons P plus. So we don't necessarily need to have Z in the symbol. It's here in this one, but it doesn't need to be there because the atomic symbol X is going to tell us how many protons there are, because each element has a unique number of protons in the nucleus. So we know that this is molybdenum. So if we wanted to, if we didn't have the atomic number directly in the symbol, we could go to the periodic table, which is somewhere here. We find MO, which is molybdenum, and that's element number 42, right here in the middle of the transition metals. So that tells us it has 42 protons. So whether that number was given to us or not, we can figure that out from the symbol. But Z is the atomic number, so if it shows up in the symbol, that's what that bottom number means. A is the mass number, so the one that's on top. And this is just the number of protons plus neutrons for that specific isotope. And neutrons we abbreviate N with a 0 because they have 0 charge. So that's A. And then finally, for a neutral element, the number of electrons, which is also part of this question, is just equal to the number of protons. For a neutral atom. So obviously if we have an ion, we have either extra electrons or fewer electrons than that, but for a neutral element or neutral atom, that's the case. So now we can just find the relevant numbers for this one. So for this symbol here for molybdenum, Z is 42, which tells us the number of protons. A is 96, and that's going to be the number of protons, which is 42, plus the number of neutrons. So if we have 96 total, we have 42 protons, we need to have 54 neutrons to give a mass number of 96. And then finally the number of electrons is also equal to 42 because it's a neutral atom that has the same number of protons and electrons. So the answer choice that then works out correct for protons, electrons, and neutrons is A up here. Okay? All right, questions on atomic symbols. All right. All right, so number 3 is the properties of electromagnetic radiation. What is the frequency and energy of a blue photon with 485 nanometer wavelength? All right, so in this question we're finding two quantities, frequency and energy. And there's really two equations we need to know that relate different properties of electromagnetic photons. All right, so the two properties, remember a photon is a little packet of electromagnetic energy. So if we have a beam of light, it's made up of a bunch of photons, and each individual photon has properties that are defined by the wavelength and the frequency. So the wavelength is the distance between the crest of the wave in a wave, and then the frequency is the number of cycles per second. All right, so if we have the two equations we need are the product of wavelength and frequency, lambda times nu is what we abbreviate them. That's equal to c, which is the speed of light. And then the other equation, which is for the energy of an individual photon, E is equal to h times nu, where h is another constant. Both h and c are on the periodic table sheet, so you don't need to remember those. We can rewrite that then, because if we combine these two equations, we can write energy as hc over lambda as well. All right, so these are two equivalent ways of calculating the energy of a photon. Which one you use depends on what's more convenient for the given situation. All right, so for this one we have a 485 nanometer wavelength. We want to find frequency and then energy. So if we're going to do these problems, remember that if we go to the periodic table again and scroll up to the constants, I don't know if we can read them from where you guys are, but all right, so these ones are at the bottom here. So this is in joules per second, that's h, and then the important one is that our speed of light, c, is in meters per second, so any wavelength we put into these equations has to be in meters. All right, so we've been reminding you about units all semester, and this is one where it's somewhat important. So we need our wavelength in meters first. Nanometers is a very common unit for wavelengths, but this time we need to convert it to meters. So it's 485 nanometers, and then remember nano means 10 to the minus 9, so there's 1 meter per 10 to the 9th nanometers. So a nanometer is 10 to the 9th, smaller than a meter, which means we can convert this to 4.85 times 10 to the minus 7 meters. All right, so that's our wavelength, and then we're going to just use these two equations to find the frequency and energy. So if we solve for frequency, that's going to be c divided by lambda. From the constant sheet, c is 3.0 times 10 to the 8th meters per second. Wavelength in meters is 4.85. So what we get here is 6.18 times 10 to the 14 hertz. Remember, so we have inverse seconds. So hertz is inverse seconds, this is the equivalent unit. And then for the energy, we can either use h nu or hc over lambda. We just found nu, so this will be maybe a slightly easier operation just to use that directly to find the energy. So if we just take that number times h, which is another fundamental constant. So h has a very small value, 6.626 times 10 to the minus 34 joule seconds. And then it's going to be that frequency which we just found. Right, so the seconds cancel out and you get joules. So it's 4.09 times 10 to the minus 19 joules. All right, so those are the two numbers. We go up here to our answer choice, and they're A again. All right, questions on those equations. All right, now keep in mind we could have problems where we use these equations by themselves as we did here, or sometimes, I don't know if we have an example of this on this one, but you might have to do the Bohr equation where you're figuring out transition energies between levels, and you have to use these equations to convert between energies and wavelengths and frequencies and things like that. So those equations could come back in other contexts as well. Remember that this final exam review is not comprehensive. It's impossible to be in only 34 questions, but trying to give you a relatively good coverage of everything, but definitely review some things on your own. The final exam questions are not designed to be more difficult than anything we've seen before, though they should look very familiar for the most part. A lot of them are very much the same or almost identical to what we've seen before, but there are a lot of them and a lot of topics that we have to be familiar with. So I'll try to get as much of them as possible, but don't think that just knowing this review is going to necessarily be enough. That's sort of my caveat for the day. All right, number 4, we're asked for the name of the orbital pictured below. So an orbital is a region in space where electron resides, has some high probability of existing in that region, and we want to know the one here. So to know what the orbital is, we first have to think about the shape. So the shape tells us what kind of orbital is, S, P, D, or F. We're not really going to be responsible for the shapes of F orbitals. But if we recall from when we introduced this, S orbitals are spherical shaped, so they just look like a sphere. Okay, so that's clearly not an S orbital. P orbitals have the dumbbell shape. All right, so a P orbital has sort of that figure 8 shape with one positive phase and one negative phase. And then D orbitals, there's two different ones, but most of them have a 4-leaf clover shape. And there's one oddball D orbital that has this shape here. We have sort of figure 8 with a donut around it. Okay? So those are the basic shapes of the orbitals. We should be a little bit familiar with those. So clearly this picture up here is a P orbital, so we can eliminate 2 of our answer choices. Now the question is which P orbital it is. And for P orbitals, it's very straightforward. The 3 P orbitals lie on the 3 different Cartesian axes. This one is clearly oriented along the z-axis, so we call it PZ. So it's on the z-axis, we call it PZ, and that gives us choice E. All right, so you should definitely know these 3 basic shapes. We're not going to probably give you specific d orbitals, dx squared, y squared, or dxy, or any of those, but you should know the basic shape of a d orbital, which is 4-leaf clover. Yes. Where it's shaded in between axes? Yeah, so it's like, 4-leaf. Oh, so that would be, so the d orbitals have different orientations. They're not just x, y, and z anymore, because there's 5 of them. We're not going to ask you about the specific d orbitals on the exam. You just need to know the basic shape of a d orbital, okay? But for the p orbitals, we could. So px, py, pz, those are pretty straightforward. Definitely be aware of those. All right? Any questions on orbitals? All right, moving on to number 5. Which of the following is a valid set of quantum numbers for an F electron? All right, so when we give you sets of quantum numbers, which are a series of 4 numbers, remember that they mean different things and they have the following format. So the first number you see is the principal quantum number n, the second one is L, the third one is m sub L, and the fourth one is m sub S. Now it is helpful to review what these different things mean, so quickly I'll give that to you. N tells us the size and energy. L tells us the shape, and if it's more than one electron, it also contributes to the energy. Okay, so in multi-electron atoms, the energy depends on N and L. For one electron, it only depends on N, so be aware of that distinction. M sub L is the orientation of the orbital. So the 3 different p orbitals that we saw on the last slide, px, py, and pz, are going to have 3 different m sub L values. That's sort of the what that number tells you. And then m sub s is just plus 1/2 or minus 1/2. It's just a property of the electron. It has no bearing on orbital energy or orbital shape. Okay, so those are the 4 quantum numbers, and you should be at least a little bit familiar with what they mean physically. But for this question, we just need to figure out which one of these is valid for an f electron. So if it's an f orbital, remember that these letters here, s, p, d, and f, they tell us the value of L, the second quantum number. So if we have L can be equal to 0, 1, 2, 3, and so on, and the ones that we find in real atoms, that exist on Earth are s, p, d, and f, and these correspond directly to those letters. Okay, so if we're if we have an f electron, that means L equals 3. So that means our second quantum number here, the second number in these series, has to be equal to 3. So any of the ones that don't have that, we can cross out right away. Okay, so this is the wrong L. And this one is the same thing too, wrong value of L. So L has to be 3, so that limits our choices to A, C, and D. And now we have to figure out which one of these is okay. So we have to remember the rules now. So n can be any positive number. N can be 1, 2, 3, 4, and so on, all the way up. And then the values of L are constrained by the specific value of n. So L can be, it starts at 0 as we showed, and then the maximum value of L within a given value of n is n minus 1. Okay? So that means in this situation that we're talking about here, L equals 3, n has to be greater than or equal to 4. Okay? So to have an f orbital, one that has L equals 3, n has to be 4 or greater, because the biggest value of L is n minus 1. So from that we can eliminate choice A, because that's an invalid value of n. So you cannot have n equals 3 if L also equals 3. Okay, so we've gotten one more of our choices out of the way. And now finally, to evaluate the last two, so these choices C and D here, 4, 3, 4, 3 are the first two quantum numbers. That's fine because it's n equals 4, so that means L could be 3, and L equals 3 corresponds to F. But now let's think about the last one, which is m sub L. This one goes from minus L, including 0, all the way to plus L, which means for an F orbital we have minus 3, minus 2, minus 1, 0, 1, 2, 3. So these are the possible allowed values of m sub L. And choice D here has a value of m sub L that's minus 4. That third number in the list for choice D is minus 4. So that's an invalid m sub L, so the only one that's left standing is choice C. Alright, so that's hopefully a good overview of the rules for quantum numbers. So definitely understand what the individual quantum numbers mean and the relationships that they can have that determine which values of the quantum numbers are permitted. Okay, any other questions on that? All right.
Can L and m sub L be equal? Like, could they be the same numbers?
Yes. Yeah, so the largest value of m sub L is equal to L, which means there will be one value of m sub L that is the same as L. All right, so number 6, we have an atom in its ground state contains 31 electrons. How many of these are in subshells with L equals 1? Enter your answer with no units. Okay, so L equals 1, remember, is a p subshell. So in this case, what we're going to do is we're going to take those 31 electrons and we're going to throw them into the lowest possible electron configuration, and then we're going to figure out how many of those electrons are in p orbitals or in p subshells. All right. So to do that, we have 31 electrons. We could just start filling in the subshells in order, but remember that the periodic table is always our friend when we're doing electron configurations. So if we go to the periodic table, we can figure out, where is atomic number 31, and how do we fill those electrons to get to there. That'll help us out, I think. So let's go to the periodic table. All right, so 31 here is gallium. So right there, atomic number 31. So we need to fill up all the electrons to get to there. Okay, so remember when we fill electrons, we start here in the first row, which is the 1s subshell. So we go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. Okay, so remember the order for subshells. So this column over here is the S block. The right hand 6 most columns here are the P block, and the ones in the middle are D. So it's going to be S, P, and D. And so as we fill in 31 electrons, we're going to have this configuration. So it's going to be gallium as the element, and its configuration is 1s2, 2s2, 2p6, 3s2, 3p6. And remember, after we do 4s2, we go through the 3d block, so that's the 3d10 part of the periodic table, and then 4p1. All right, so review that concept because electron configurations will come up on 1 or 2 questions. And then for this one, we just want to know how many of these electrons out of the 31 are in p subshell. So we have 2p6, we have 3p6, and we have 4p1. So we have a total of 13 p electrons. Okay. Questions on electron configuration? Yeah.
If you were to do a shorthand for that, would you still get the same answer?
Well, you would get the same answer, but you have to remember which of those p electrons are buried in the noble gas configuration. So the shorthand for this would be, I think it's argon. Yeah, so it would be argon, and then 4s2, 3d10, 4p1. So if you write the shorthand configuration, the 2p and 3p electrons are going to be buried in these core electrons. So you have to realize that they're there and still count them. So for this one, it's probably easier just to write out the full configuration. And you know, do be aware that when we give you electron configurations on the test, obviously these types of problems are usually going to be multiple choice or something like this, where you just have to answer one little thing. We're not going to have you write the whole configuration. But you should be familiar with both the longhand notation, which lists every single subshell in order, and the shorthand notation where you list noble gases in parentheses that represent the core electrons that come before the valence subshell. Okay, so both of those notations could be used, and they both have their value depending on what context you're talking in. Okay. All right, so hopefully some fond memories are getting conjured up as we go through these old things. All right, so let's go on to number 7. All right, this one I don't think we talked about a whole lot, so I do want to cover it here. We want to know which of the following is an excited state configuration for a phosphorus atom. All right, so the first thing we should look at is, we're talking about phosphorus here. We should be familiar with the atomic symbol for phosphorus, which is P. And if we go to the periodic table, phosphorus has 15 electrons, so it's right here next to next to sulfur in the third row of the periodic table. So there's phosphorus. So we need to sort of understand what an excited state means. We've talked about excited states just a little bit, but not so much in the context of multi-electron atoms. So when we say excited state, here's what we mean. It means we have one or more electrons moved from the ground state position to higher energy. Now a couple key points about this. So we know the ground state configuration is what we predict using the periodic table and Pauli exclusion, all those rules that we just followed in the last problem. That gives us the ground state. In the excited state, we're going to take one of those electrons and we're going to move it up to a higher energy subshell that's currently not filled. All right, so a couple key considerations. If you're evaluating what is an excited state, what is which of these answer choices works, you have the same number of electrons as the ground state. So we're not adding or subtracting electrons, we're just moving them into higher energy positions than where they started. So it's the same number of electrons as the ground state. And also we need to still follow Pauli exclusion rule. So you can't violate this rule. You're going to violate, in some cases, Hund's rule or the Aufbau principle. Those get violated in excited states. But the Pauli exclusion, which is 2 electrons per orbital, that one never gets violated. So we can still have no more than 2 electrons per orbital. Okay, so if we look at these configurations here, choice A, 1s2, 2s2, 2p6, 3s2, 3p3. Okay, that's 15 electrons. That's the correct number of electrons. But this actually, as it turns out, is the ground state of phosphorus. Okay, so this is the configuration we get by following all those rules and working through the periodic table. So this first configuration here, A, is the ground state. So an excited state configuration should be something different than that, where one of these electrons, or possibly more than one of these electrons, is bumped up from one of these positions into a higher, currently unfilled position. So if we go to choice B, 1s2, 2s2, 2p6, 3s1, 3p4. So what we've done in choice B is we've taken one of these 3s electrons from the ground state, and we've moved it up into the 3p orbital, which is not completely filled yet, the 3p subshell. So this one counts. This would be an excited state. We've taken one electron from S and moved it into P. But we're able to do that because, again, the P subshell in the ground state is not filled, so it can take still 3 more electrons. And if we go to choice C, we've done just one more. So we've taken this second 3s electron and also moved it up and made it into another P electron, 3p5. So still 15 electrons. We still haven't violated the filling rule, so this one is an excited state. Now let's look at choice D. So choice D has 18 electrons. We've taken the ground state, we've added 3 more into the 3p subshell. So this is the configuration for P3 minus, which is an ion, not an excited state. Remember, an excited state does not have extra electrons or is not deficient in electrons. We're just moving them around. Okay, so choice D is a ground state also, but it's the ground state for the P3 minus ion. Question in the front.
Is it accurate to say that the ground state is the most stable?
Yes. Well, that's one of the reasons. So when you predict the ground state configuration for any atom, whether it's this one or any atom on the periodic table, the ground state is the most stable or the lowest energy configuration. And there's a lot of reasons why that is. So we talked about the different rules for filling. So one of them is off-bound. You're filling lowest energy to highest energy. So you want to put all the electrons in as low of energy position as possible. And then Hund's rule, which doesn't really come into play here because we're not considering the actual spins of these, but remember that we fill the orbitals one at a time. That contributes to stability because of a quantum mechanical principle called pairing energy, but it also, because it's half filled, that's why half-filled subshells with one electron in each orbital do have good stability. So yeah, all those reasons contribute, but anytime you predict the ground state, it is in fact the lowest energy or the most stable configuration. That's another important consideration. So choices B and C, which are excited states, so our answer is going to be E then, but these are 2 higher energy configurations. So these are going to be higher in energy than the ground state. If we want to get from the ground state to the excited state, we have to put energy in, usually in the form of electromagnetic radiation. Okay? Other questions on this topic? All right. Good. All right, question 8. Which of the following is expected to have the smallest third ionization energy, i.e. 3? So remember that ionization energy, we have an atom, and we're going to just remove an electron from that atom to make the cation. So it's the energy associated with pulling off an electron from an atom, and each ionization energy is successive. So this would be the first ionization energy. We're removing the first electron. The second ionization energy is removing the second electron, so we're taking the cation, removing another one to make it 2+. That's ionization energy 2. And then ionization energy 3 will be going here. So we have successive ionization energies, which we refer to removing one electron at a time. As we go down the list from ionization energy 1 on down, they do get higher every time because it's more difficult to remove an electron from a positively charged species. However, as we talked about, there's going to be a huge jump once we start removing core electrons. So we have to think about how many valence and core electrons, or more importantly, how many valence electrons do all these things have. Removing valence electrons is relatively easy. If you start removing core electrons, it becomes increasingly and exceedingly difficult. So when you're evaluating ionization energies, there is a periodic trend. It increases in general as you go up and to the right. But if you're evaluating a ionization energy besides the first ionization energy, IE2 or IE3, it's important to first think about how many core electrons how many valence electrons each of these things have. Because if you're ever removing core electrons, that's going to elevate the ionization energy, and you would want to sort of assume that that's going to be the highest one, regardless of periodic trends. All right, so if we look at our choices here, sodium, the configuration is neon 3s1. And so this has one valence electron. It's in the first column of the periodic table, so everything in that column has one valence electron. So if it only has one valence electron, the third ionization energy, i.e. 3, refers to removing a core electron. So it's going to have a very large third ionization energy. Okay, we can't directly use the periodic trend to predict third ionization energy because it partly depends on how many valence electrons we have and whether we've already removed those or not. For boron here, there's 1s2, 2s2, 2p1. Okay, so remember valence electrons are all of the electrons in the outermost shell. So those are going to be for p block elements, the 2s and 2p outermost electrons. So boron, which is in this column of the periodic table here, group 3a, group 3a tells us that it has 3 valence electrons, the s and 2p electrons. So it's going to be 3 valence electrons. So that means the third ionization energy for boron, we're still removing that last valence electron, which means it could be comparatively easier. And then if we go to aluminum, aluminum is just below boron on the periodic table, so it's going to be also S2P1. This also has 3 valence electrons. All right, and then the last two are magnesium and calcium. So both of these are in group 2 of the periodic table. Magnesium is neon 3s2, and calcium is argon 4s2. So both of these have 2 valence electrons. And again, since we're talking about the third ionization energy here, we would also be removing core electrons from these as well. They only have 2 valence electrons, so removing the third electron has to come out of the core, the noble gas core. So that's going to be a large third ionization energy. So in this problem, the only 2 choices that don't involve core electrons are boron and aluminum. So now we have no choice but to look at periodic trends, because in both of these we're removing the third valence electron. So now we have to think about how does ionization energy depend on location on the periodic table. And for these ones, boron and aluminum, we would predict that boron is greater than aluminum, because ionization energy increases as we move up a column. Okay, so in other words, for boron, we're removing that last valence electron, which is 2s, and that's going to be held more tightly to the nucleus than the 3s electron in aluminum, which is farther away from the nucleus and has a lower ionization energy. So in this case, now that we have 2 choices where we're both removing valence electrons, now we can use periodic trends and think about their relationship. And boron is above aluminum, so it has a higher ionization energy. So if we're looking for the smallest third ionization energy, that would be aluminum. Okay, so boron is greater than aluminum. The rest of these are all expected to be much higher because they're core electrons, so aluminum is the one that would come in as the lowest. All right, so that sort of brought in 2 concepts. You need to know the periodic trends for ionization energy as well as how the number of valence electrons affects things as well. Okay, questions on that? All right. All right, so number 9 is dealing with atomic or ionic radius. So when we're dealing with atomic radius, there's also a trend, as you know, sort of the opposite of ionization energy. The radius increases right to left, and it also increases top to bottom. Okay, so we have that periodic trend. Remember, that only applies to neutral atoms. If we're talking about ions, we need to also think about their configuration to understand things about their size. Because as we're removing electrons or putting electrons in, we're going to influence the radius. So the first thing we should do when evaluating ions is look at the configuration. So if we have calcium 2+, calcium is here, number 20, and so removing 2 electrons takes us to argon. So calcium 2+ has the argon configuration. K+ has the argon configuration. It's also right next to argon. We move 1 electron to get there. Argon, of course, has the argon configuration. Cl- has the argon configuration. Okay, so all of these first 4 choices have the same electron configuration. They have 18 electrons, and they have the configuration of argon. And then Br- is a different one. That has the configuration of the next noble gas, which is krypton. So Br-, bromine is here, number 35. and one more electron takes us to krypton number 36. So this has a different configuration. So to compare the electrons that have the same configuration, all we need to look at is the charge. So choices A through D are what we call isoelectronic, which means they have the same number of electrons. Iso means the same. So when you have isoelectronic species, whether they're atoms or ions, if you have more negative charge, that's going to give you a larger ion. Okay, so the more negative charge you have, the larger it is, because they have the same number of electrons, and the one that has more negative charge has fewer protons in the nucleus to pull those electrons in. So we have the one of these choices, the one that has the most negative charge is chloride. So for A through D, Cl minus is the largest. Now we need to compare Cl minus to the last one, Br minus, which has different numbers of electrons. Okay, so typically speaking, when you move down the period, or I would say all the time, when you move down a row in the periodic table, you're going to make it larger. So bromine, you're filling now the 4p subshell. So this is going to have a larger radius than chloride, which has only 3p occupied. So as you move down the periodic table, it's unambiguous that you're going to be increasing the size. So that means bromide is larger than chloride because the radius increases down a group. And so that means our largest one overall is going to be choice E, which is bromide. Okay. Now that one probably was, maybe a little bit more thought than necessary, because all of these are just 3p valence electrons. This is 4p. So with that information, you would predict that the 4p is going to be larger. But hopefully this helped you rationalize through these first four, and then we just compare that largest one to that. Yes. Yes, the smallest one would then be calcium 2+, because that has the most positive charge. So when you're comparing isoelectronic ions, more positive charge equals smaller, more negative charge equals larger. Okay. All right, and then finally number 10, probably the last one we'll do in this session before migrating, or maybe just staying here. I don't know if anyone else is coming here or not. Which of the following ionic compounds is least likely to occur? All right, so this one essentially what we're asking is, did I change this? I thought I changed some of the choices here. Okay, let me change some of these answer choices because I thought I did, and apparently I didn't put in an updated file. Yours is changed. So this should be magnesium phosphate, right, or MgPO4. And this one is AlCO3. Okay, I forgot to change it in my version. Sorry about that. Okay, so those are the correct answer choices, because we didn't talk about p-block or transition metal cations in a lot of detail, so we're not going to ask you detailed questions about those like this. All right, so here we're looking for which ionic compound is the least likely to occur. So when we're evaluating whether an ionic compound can occur or not, we need to think about what is the charge on the ions in the structure, and does it represent a stable cation or anion for that compound. Okay, so if we look at choice A, we know that sodium likes to form +1 charges, bromide Br minus, so both of these would work out. So sodium bromide is in fact a stable ionic compound. It has a +1 sodium, which is the charge that sodium wants to have. It has a -1 bromide, which is the charge that bromide wants to have, so that one works. Choice B, we have magnesium and carbonate. So I think for these ones it's best to start with a polyatomic ion. Let's assume that our carbonate has its normal charge, which is 2-. So we have to remember our polyatomics. So carbonate is 2-. So if we have a 2- anion, that means we need, if it's MgCO3, just a 2+ cation. And that works out because magnesium is in group 2 of the periodic table, so it wants to be +2. So this one works out. Okay, choice C, the one that I edited, this is MgPO4. Okay, so PO4 is phosphate. Does anybody remember the charge on phosphate? I've heard of 2 and a 3. I like 3 better. So phosphate is 3-. Okay, so if we have a 3 minus phosphate anion, that would mean in order for this formula to be true, MgPO4, your magnesium would have to be 3 plus. Okay? And remember that magnesium only forms 2 plus cations. Okay, so that raises a red flag. And then finally for choice D, we have aluminum and 3 chlorides. So chloride, if we assume that that's -1, that would make our aluminum +3. And one that we should be aware of is that aluminum only forms +3 cations. I don't think we talked about that one as much, but aluminum is here on the periodic table, atomic number 13. Okay, so aluminum is going to lose the p electron and both s electrons to form a +3 cation, which is very stable, gives it a noble gas configuration. So aluminum +3 is what that'll form, so we should be aware of that one. And then finally for barium hydroxide, we have 2 OH minuses, so a total of -2 charge on the anions, which would give us a +2 charge on the cation. Now if you wanted to, you could have assumed that the cation had the correct charge and then figure out what would the charge on the anion be in that situation, figure out which one's wrong. But however you look at it, choice C here has the incorrect balancing of cations and anions. So if you were going to have a compound of magnesium and phosphate, it would have to be Mg3PO4 taken twice to balance the charges correctly and form the stable +2 cation for magnesium. Okay, so that's how we evaluate that one. Remember how we can use the charges on ions, we can predict most of them, and then once we know the charge, we can predict the formula correctly. All right, I'll wrap up there. I'll give everyone a chance to leave that needs to go. I'm thinking about just staying here because I don't think there's... Is anybody in the ACS group? Do they have a meeting afterwards? No? So that's the only group that uses it on Friday besides us. All right.